With 34 people already in.
Perfect. Okay, good morning, everyone. We've got a good number already joined up, so I think we're just about ready to make a start. I've just got some very brief points my end before we get started, so that should give people enough time to join if anyone's joining late. So, yeah, good morning, everyone. You're all very welcome to today's Foresight webinar. This session today is looking at the UK's fusion industry landscape. Really excited to get into this one. My name's Tiernan Phipps. I'm lead producer for the Foresight webinar series. It's my pleasure to welcome you all this morning. As I said, over the next hour, we'll be taking a deep dive into the fusion landscape here in the UK and beyond, looking at sort of both its potential for clean energy and clean power, looking at the Clean Power 2030 mission and the industrial strategy and other policy levers as well. But we're also going to be looking today at its current applications as well within the medical field. We're going to be looking at what work is going on around fusion right now in terms of market applications and creating a bit of a business case for fusion as well. So two fantastic speakers joining us today. Dr. David Kingham, who is Executive Vice Chairman at Tokamak Energy. So David and Tokamak Energy, for those of you who don't know, are working on compact spherical tomahawk power plants, and I'm sure David will be able to go into
Tokamak. Yeah,
Tokamak. Yes,
I like tomahawk though. That sounds cool.
Did I say tomahawk?
Yes.
Well, there we are.
Yeah.
I've got new ideas clearly for the industry. Yes, Tokamak power plants, but as I said, David, you'll be able to do it a lot more justice than I will. On the other side, then Talmon Firestone as well, CEO of Astral Systems, and as I said, Talmon and Astral are making vital medical isotopes and applying them in kind of the real world medical field right now as well. I think modular devices as well, so close or at the point of where they're needed as well. So that's really interesting. I'd like to hear a bit more about that as well. So yeah, put together, I suppose they tell a bigger story that fusion is both an incredibly exciting future power source and a tool for industrial and healthcare innovation as well, with real world tangible benefits right now. So what we'll do today is we'll hear from both speakers for about 15 minutes. I've got some questions on my end, and then we're going to open it up to questions and comments from the floor as well. So please feel free to pop any questions that come to you into that Q&A function up at the top of your screen there, and I'll make sure that they get asked to the speakers as well. A couple of final things from me. Just a reminder that this session is being recorded, and a recording will be sent around and circulated post event, so do keep an eye out for that. It should be with you all later on this afternoon. We'll also be sharing a LinkedIn takeaway blog post and a blog post as well, so do check those out as well if you want a bit of a recap on what was discussed this morning. Finally, this session is sponsored by the Foresight event, our all energy conference and exhibition taking place on the 4th and 5th of February. If these discussions are of interest, please do consider checking that out. We'll be discussing fusion, we'll be discussing SMR technologies and wider renewable and clean energy markets as well in that conference. We've also got the next gen nuclear and data center energy summits taking place next year as well, where we'll be going into a bit more detail about these discussions as well. So do feel free to check that out. I'll pop some links in at the end if you want to see what we've got going on there. But with all that boring stuff out of the way, really happy to hear from both of our speakers now. We're going to hear from David first. So David, I will hand over to you. The floor is yours. Go ahead.
Thank you very much, Tiernan. Let me see if I can share the correct screen. Well, it looks quite promising. Can you see that okay?
All clear, David. Go ahead.
Yep. Now, I wonder if I can Is that showing full screen for you?
It is indeed. Yep, that's full screen for us.
Okay, great. So the story of Tokamak Energy as of today. Yeah. So we are a fusion energy technology developer. We have a view that the spherical tokamak with high temperature superconducting magnets is the optimum way to commercial fusion energy. And we are on a path which both delivers new near-term revenues, and we see a whole profitable path to our participation in development of commercial fusion. So what do we do? Well, we build real devices to demonstrate new technology and push things forward. Let me see if I can get some videos to play. Sorry, I'm having a little trouble navigating around this. Now, can you see those videos? Hopefully
Go ahead.
They're showing full screen nicely. So what's going on in the left there? So this is our high field spherical tokamak known as ST40. The basic reaction that's going on there is a deuterium fusion reaction. The plasma temperature is getting up towards 100 million degrees at the hottest part of the plasma. This is a film taken with a camera operating at 16,000 frames a second. So you're obviously seeing a slowed down version of the evolution of that plasma. The plasma duration is about a quarter of a second. So we can study, using this fast camera in correlation with all our other diagnostics, we can study what's going on. And what's happening in this particular experiment is we're dropping lithium into the plasma. So the top right of that video, you can see red, what looks like red dust, really. So that's lithium initially going into the edge of the plasma. And then later on in the pulse, you can see some green, and that is ionized lithium being propelled around the magnetic field lines in the plasma. So here we go again. The red to start with, then it gets ionized. Then once it's ionized, of course, the lithium follows the magnetic field lines and travels, accelerates very, very rapidly. And the point of the experiment is because we think that lithium will be crucial for future commercial fusion to enhance the performance of the plasma, to protect some of the first wall surfaces that see the plasma. So we're embarking on a major program to develop this lithium-related technology. The other, now will it show as a video the other? Hopefully that's showing as a video. That's our magnet system. We've just announced the first results from this system, where we've achieved 11.9 Tesla on the, sorry, that's hopped back. So this is a magnet assembly, high temperature superconducting magnets in the configuration necessary for a fusion power reactor. It is approaching the current density, the forces, the magnetic fields necessary for commercial fusion. There's a little bit further to go, but we're already putting 7 million amps through the center column of that device. On test at the moment, tests are going very well. They are crucially demonstrating different magnet technologies embedded within this system. So you can imagine it's pretty exciting actually building this hardware and making sure it works okay. So a bit more about the business. Essentially, we now have two business units. We have a fusion energy business unit aimed at government as customer, and we have a TE magnetics business unit looking at many applications of high temperature superconductivity. Originally, this was just magnets, but more recently, we've been looking at power distribution systems, for example, for data centers or DC grids. And this on its own is a very large commercial opportunity. And we're aiming really to be the first in the world to demonstrate significant commercial traction with high temperature superconductivity. So how do we position ourselves here for the high temperature superconductivity? Well, we've got a lot of inventions, and we've turned those inventions of how to make the magnets, how to stack them together, how to control them, how to tune them, configure them, how to manufacture them. That's all coming together into a significant technology stack. And we can then harness the fundamental advantages of the material. So basically, the high temperature superconductors work at much higher temperature than conventional superconductors, typically 20 Kelvin or higher compared to 4 Kelvin. So 20 Kelvin is still pretty cold, but it is relatively easy to cool magnets to that temperature. They can then carry much higher current, generate much higher magnetic fields, like double the magnetic field strength. And we recently have worked out how to ramp up those magnets very rapidly and ensure they're mechanically very tough. So this technology is going to go into many markets in future. So as far as industrial strategy is concerned, we believe that pursuit of fusion energy, although it may take a while, is going to throw off lots of other technology opportunities. And from our perspective, the high temperature superconducting magnets are really the big one. I'll go on to explain a bit more about the different applications that we see. Yeah, just some pictures here of the maturing of our intellectual property into hardware, prototypes, demonstrators. You'll see there a high current, high temperature superconducting buzz bar. In our demo 4 magnet system that I showed earlier, we have 7 million amps going through the center column of the device. So that's 500,000 amps through every individual magnet. So we do know how to get high currents through these high temperature superconductors. So we then look at the market opportunities for high temperature superconductors. Now, fusion itself is a big market opportunity. In the long term, as I said, we think high temperature superconducting magnets in low aspect ratio or spherical tokamaks will be the winning technology. But there are many other magnetic fusion configurations that people are working on where high temperature superconductors can be absolutely crucial. And we're working with several other fusion companies on that technology development. So we took the decision a while ago to work with others rather than pursue a lone path on our own. The next application is power systems, particularly driven by the ongoing and strengthening enthusiasm for AI. So the result of this is data centers are becoming more and more power hungry, more and more power dense. So the current required to get to each rack, the energy required to get to each rack is rapidly increasing to the point where it'll be a megawatt per rack within the next couple of years. At that point, it is worth investing in high temperature superconducting busbars to get the power to where it's needed and to avoid wasting a lot of energy. Then another application, life sciences, where my particular favorite is proton beam therapy. It can be enabled by these new high performance magnets. We have a defense application that's been publicly announced for magnets for submarine propulsion, magnetohydrodynamic submarine propulsion with General Atomics in the States. And then propulsion, we see high temperature superconducting magnets being very valuable for electric aircraft of the future. So yeah, the two biggest opportunities as we see them at the moment are these power systems and life sciences, particularly, as I said, proton beam therapy, and well, we have some commercial traction there as well, which certainly helps. Yeah, I mentioned this, the rationale for why high temperature superconducting busbars will be valuable in data centers. This is some of the analysis of the increased energy demand of the centers, the increased power to a single rack. So we see in the medium to long term that the data centers will operate with DC grids rather than AC and then convert at the rack, because the chips themselves want DC. And given the big trend for electrification, the overwhelming trend globally for much higher electricity usage, we think copper itself is going to come under supply and demand pressures, and that is also going to drive the demand for high temperature superconductors, which use a small amount of copper to very large effect, very great effect. Yeah, so massive savings with high temperature superconducting busbars. And our strategy overall here is to move from prototype to production. So we recently acquired a company, Ridgeway Machines, who make machines to automate magnet winding, among other things. And we've announced a Japanese joint venture manufacturing facility with Furukawa Electric, who are a strategic investor in Tokamak Energy. So in the fusion energy side of things, I'll move quickly. We see partnering with government as the way forward. We'll develop our own technology, but we're looking for these national and international partnerships. For example, the UK and US governments are supporting our lithium program on ST40 over the next 3 years. That's a $52 million project. We're working closely with the STEP team, UK industrial fusion solutions. So aiming to work even more closely with them in the future. We've just announced a collaboration with CAXT, the research center in Saudi Arabia, to pursue fusion and high temperature superconducting technologies. We're involved in a project in Japan called FAST, Future Advanced Superconducting Tokamak, and we're involved in the US Department of Energy Milestone program. So plenty of interaction with government there. I mentioned this LEAPS program, lithium on ST40. So really, we see public-private partnerships as the optimum way to pursue commercial fusion energy, and we can play our role in those partnerships. And yeah, we're very much a business these days, not just a technology developer. So I won't go through this in detail. The point is we have a revenue model for both sides of the business, TE Magnetics and the fusion engineering and fusion innovation side. So I will finish at that point.
David, thank you very much.
Work out how to unshare the screen.
There should be a stop sharing button, but regardless, Talmon will be taking control very soon. David, that was really interesting.
Okay. Yeah.
Thank you very much. Yeah, great. I think those videos are fascinating, even just to see the process kind of happening, or part of the process. It's it's that's amazing, and also just to see all of these different applications and potentials for this technology as well, specifically that magnet technology. There's certainly quite a few avenues to explore there, which is really good to see, even outside of power as well. So and I'm sure, as we mentioned, Talmon will kind of go into a bit of that as well. I suppose just really quickly, I just want to ask you a question on this. You mentioned now that outside of being a technology developer, you're very much an industry member now, and part of a market. Do you sort of have any views on? Obviously, we've got STEP now. We've got kind of regulation following in terms of BN8 skills. Do you see how this fusion market kind of shapes up as an industrial strategy, not just kind of as hard science? How does that shape up in the future? What are the key things that need to happen in order to really help this industry kind of move forward?
Well, I think two things really. One is government as customer to stimulate industry as a supplier. So the STEP program, UKIFs are set up in that way. UKAEA is also increasingly buying products and services from private companies. We think alongside that, there still needs to be more radical innovation, for example, in materials development for fusion. But that will need some public funding. And the second part of it is definitely the spin-out technologies, such as high temperature superconducting magnets, which will demonstrate to government that its expenditure on fusion, which is quite substantial and has been for decades, is resulting in economic growth and more jobs in the UK. We think the high temperature superconductors and the high temperature technology for things like data centers are the key demonstrator of that, but there will be other demonstrators. There are other spin-out companies from fusion getting established. So yeah, it can be a rounded part of an industrial strategy.
Yeah. I think just on that point, it's well known the UK's capabilities in terms of research and development. We have some world-class research facilities. Where we tend to fall short is keeping those companies in this country as well. We've seen it in a few industries where
Yes.
we can't quite grasp the benefits of that R&D. Very broad question. Any thoughts on how we use fusion as a catalyst to kind of change that narrative as well, here in the UK?
Yes, supply of private capital is for scale-ups. I mean, we're now 320 employees. We've raised about $350 million, going very nicely. We need to raise some more to really maximize our economic impact, maximize our value. And it is certainly easier to raise money for things like fusion in the US than it is in the UK or Europe or anywhere else in the world. The US just has that supply of scale-up capital. So what can be done about it in the UK? Well, one thing that could be done is to get pension funds to invest more in the UK. They used to do that, but over the last 15 years, they've tended not to. There is a thing called the Mansion House Accord, which is an intent by major pension companies to invest more in the UK. But I'd like to see that really happen, and for some part of that investment to go into technology and scale up of technology. We're pretty good at funding initial spin outs, but really not good at scaling up.
And I suppose just on that, seeing as you've done now, kind of demonstrating that technology working, and Talmon in terms of the tritium breeding equation there, kind of showing these success stories is really important as well. Final question before we hear from Talmon, then I just want to really quickly delve into a bit of sort of the demand side levers part of the equation and kind of that de-risk aspect. Do you see sort of any potential and room for kind of either advanced market commitment or sort of a CFD approach eventually for this technology from the government side? Any thoughts?
Oh, I think that will come, but I think more evidence is required from both government laboratories and private innovators to give a clear sight of a viable commercial fusion reactor.
Yeah, absolutely. David, thank you so much. If anyone does have any specific questions for David, please do pop your questions into the Q&A tab there. We will have a bit of time at the end for Q&A. But for now, David, really good to hear what's happening on your side at Tokamak, not Tomahawk, at Tokamak Energy. Thank you very much. Talmon.
Thank you.
Thank you very much, David. Talmon, we'll hand over to you now to hear a very different part of the fusion equation, but really looking forward to it. I'll hand over to you. The floor is yours.
Thank you very much, Tiernan. And I'm, as you can see from my cover slide, and which is kind of similar to David's cover slide, I'm glad to see that we're showing real pictures of real plasmas, fusion plasmas now. A lot of over the last number of years, a lot of fusion presentations were made up of 3D graphics or concept art. Now we're at a stage in fusion development where we get to show real hardware and real pictures. So, a quick introduction. Where Tokamak is kind of one of the most famous fusion companies in the world right now. Astral is a fairly young up-and-comer, although we were formed in 2021. We are Bristol-based, and we're a developer of compact fusion reactors. Now, when we say fusion reactor, a lot of people say use the term fusion synonymously with power reactors. In our case, we're not immediately going for power. We might one day, but that's not our focus. Rather, our devices are operational today, as you can see in this photo, and there are a lot of applications, commercial applications, that can be used with the neutrons that come out from a fusion reaction. our devices actually operate continuously. So I'll start off by explaining the underlying technology. So there are two aspects to our tech. The first is that the underlying, or what the driving force is, called inertial electrostatic confinement fusion. So there's no magnets involved. Rather, you could think of it as a very fancy light bulb where you've got a vacuum chamber, and within that vacuum chamber, there's an electrode or a filament that delivers high voltage. And within the vacuum, or you make it a very poor vacuum with deuterium or deuterium tritium gas, the high voltage creates an electrostatic field which strips the electrons from the nuclei, and the bare nuclei will form a plasma, and a fusion will occur. Now, I've actually been in this business for 20 years. Astral is my second fusion company. It was at my first company in Germany called NSD Fusion where we had commercialized this type of IEC reactor as an industrial neutron source. But the performance of those systems was always limited, as IECs have always been seen as a kind of an inefficient way of producing a fusion plasma. Now, this is where NASA comes in. In 2020, a team at NASA led by Larry, who's on the right of the photo, and Teresa Benyo, who's in the center of the photo, they had been doing research into an alternative pathway to producing fusion within a solid material. And the reason they'd even been interested in this line of inquiry comes from evolutionary cosmology. The models that we have, the physics models that we have when we look out into the universe to explain heavy element production from stars as they go supernova, did not match up with the abundance of heavy elements that we actually observe in the universe. And so the community had said, why is it that our fusion models for stars don't line up? And what the realization was that 99% of the fusion that occurs within a star occurs within the most dense, innermost dense 1% of the volume of a star. It's within this central region of any star where you see very, very high density plasmas. But the density is around 150 grams per cc, cubic centimeter, within our star, far more dense than any solid material that you'll find on the Earth. And so what the community had estimated or posited that perhaps the environment within this high density plasma, where you see the free flowing electrons, is actually closer to a solid material. And the NASA team had conducted an experiment in which they introduced deuterium gas into a series of different metals, but primarily zirconium and erbium deuteride. They created these deuterides, and they were able to use a roundabout method to induce fusion within this solid material. And so they proved that you can induce fusion in a solid and at a very high density. And density is really important here, because in a plasma, the type that you'd find in magnetic confinement or other types of fusion projects, the plasma is closer to the density that you would find in the outermost shell of a star. So Tom Wallace-Smith, who's got the glasses in the photo, he's my co-founder, was a PhD student at Bristol University. And during his research, interestingly enough, unrelated to fusion, but he got side interested in fusion, had read the paper and realized that if you can add a deuteride to the inner surface of a traditional IEC type device, you might be able to dramatically improve the fusion. So this takes us to the right side here. I talked about the sun. Our devices are kind of like a sun in reverse, where the low density plasma is found within the inertial electrostatic type device, and we've put high density deuterium, into the inner surface of the chamber. So that plasma acts as a spark plug that drives a secondary fusion effect within the solid metal, and we call that multi-state fusion. It's fusion occurring in two states of matter. But we've accumulated over 1,000 hours of fusion time, and it kind of validated this that this approach works. And we're at a point now where over 99% of the fusion is attributed to the solid state within the within that surface effect. And only 1% of the fusion from our devices comes from the plasma itself. So that leads to a question of what kind of a business do we want to create? Given that we have a continuously operable fusion device, doesn't just run in pulses, but you can turn it on and turn it on for hundreds of hours. The product that comes out of that is either deuterium neutrons, which is 2.445 MeV neutrons, or DT. We to date we've only done DD, but within the next couple of months we'll be shifting over to deuterium tritium fusion. But because we're able to operate continuously, we're a company that is driven not only on data, but experiments, driving experiments. What can we put in front of these devices to get results, scientific results? Also, as a business, we could iterate. Our systems are very compact. I'll show you a picture a little bit later. They're very compact. You can build multiple very, very quickly, and you can iterate quickly. So for us to build a revenue stream, the equation is an optimization, like to say, of hardware measured by capex and opex against revenue. And we like to joke inside the company that we're focused on financial break-even before energy break-even. So this is an example of an experiment. Our neutron source, or our fusion reactor, is this cylinder at the center. We've got a detector here, and this is a lithium tritium breeding rig. This was based on a commercial contract with the UK AEA around the grand problem of how do you breed tritium, as the fusion power plants of the future are going to have to breed their own tritium as they consume it, because currently there's only about 32 kilograms of tritium on the planet, and that's only enough tritium to run one power reactor for about a month. So if I could take a step back from this slide, even to say that whenever most people read about fusion in the media, the focus has always been on when does fusion achieve energy break even? When can we get more energy out of a device than we can put in? But there are 3 or 4 true grand challenges that are equally difficult. Where energy break-even is one. The other is, can we breed tritium at a rate higher than we consume it? The other is, can we build reactors with materials that'll survive the high neutron environment? And then can we establish a remote handling system that can replace parts that can also survive in the radioactive environment within a reactor that has been activated by continuous operation? So the UK AEA has put quite a bit of investment into tritium breeding, and earlier this year we became the first fusion company to use our own fusion neutron sources to breed tritium. I should say that it is a validation. We didn't breed more tritium than would be consumed, but it was a world first. And just as a very interesting side note, this bucket over here contains a type of fungus from Chernobyl that thrives on a radiation environment. So we have other experiments. So we're always taking in scientific research from around the world. And just as a curiosity, this is a novel fungus that grows toward radiation sources. So it has evolved to consume radiation as an energy source. So here is an example of a commercial system. This is also Dr. Hugo Dominguez. He's our lead tritium breeding researcher. But you can see that our systems are quite compact. And what that also allows us to do is we can create very high flux environments. So if you allow me to get technical for a moment, there are different ways of looking at the neutrons that come out of a fusion reactor. There's total neutrons per second, but there's also total neutrons per centimeter squared per second. That's called flux. You can kind of think of it as the brightness of a light bulb. In this case, it's a fusion light bulb that produces neutrons instead of light. And so not only does the induction of fusion within the solid state allow us to get that flux very high, that density of neutrons very high, but we can also arrange our systems in arrays, tightly packed arrays. So we've got an example of a 3D print on the desk here, or I've got one on my desk. So we call our systems fusion fuel rods. They're very similar to fission fuel rods in geometry. And that in that kind of center volume that you'd see on the desk within here, you can get a very high flux, and we call that a neutron oven type design. And where that really becomes valuable is in the production of medical radionuclides. So that I talk about our business stages. We've been doing R&D. We are just a couple months away from selling or delivering the first few systems to customers, neutron irradiation services. And also we offer to the fusion community the opportunity to do component qualification. So will the magnets, will the other components that go into a fusion reactor survive within a high neutron environment? Now, I'll also take a bit of a sidestep here to talk about medical isotopes. Why medical isotopes, and why is that relevant to the UK? So traditionally, nuclear medicine has been served by fission reactor produced medical isotopes, but the UK no longer has any operating fission reactors. The UK, in fact, used to be a pioneer in nuclear medicine, but that has unfortunately shifted in the previous decades. And we now find ourselves in a position where 85% of the world's medical radionuclides are produced at 6 fission reactors around the world. 4 of them are in Europe, 2 in the East, 2 in the West, 1 in Australia, and 1 in South Africa. And of those 6 reactors, 5 of them are so old that they have to be decommissioned in the early 2030s. And so the UK government already in, I think it was 2019, had written a report, a warning that by the 2030s, there will be a significant supply shortage. And unfortunately, momentum within governments, not just the UK, but globally, has resulted in only 2 new reactors being commissioned and built, 1 in the Netherlands and 1 in Belgium. And both of them are due to come online in the early 2030s. But even if they come online in time, the world will see a 2/3 global shortage of isotopes. Now, the situation is actually a lot more dire in the UK, where we import 90% of all of these isotopes that are used both in diagnostics and in therapeutic applications. And I know it's very unpopular to speak like this, but unfortunately, Brexit turned the UK into a third-class citizen when it comes to the supply chain from isotopes coming from Europe. So what we're trying to do at Astral is redevelop a domestic capability, a strategic capability within the UK to produce isotopes within the country, particularly from the neutron produced perspective. David had talked about proton therapies. Diagnostic nuclear medicine is served by linear accelerators that produce protons. Protons produce a certain menu of isotopes, but it's fission reactors traditionally that have been your reliable neutron sources, and we're now using fusion without fissile material to produce the neutrons that we can use to generate isotopes. Now, beyond that, neutrons can also be used to transmute nuclear waste into kind of high-level nuclear waste into intermediate-level waste. So you take the storage problem of being hundreds of thousands of years or millions of years to hundreds of years. But the interesting thing is that once you've got fusion neutrons onto fissile material, that fissile material acts as a neutron multiplier. And that's why we actually believe that that a very rapid and economically viable path towards fusion power is through fusion-fission hybrid applications. And you'll see again in this 3D print, we've changed the color of the inner ring. This could represent a series of fission rods, where you use the fusion neutrons on the outside ring to hit the fission material on the inside, and that multiplies the neutrons. Now, that whole topic can become a 30-minute discussion of its own, so I'll just pass on quickly. But just to say that this is one of the directions that we're interested in going in. So kind of in summary, or actually a few more points to say, we have our first 6 commercial fusion reactors are being assembled right now. The first will be assembled in December, just in a few more weeks, with the whole batch done in January. We already have our two first customers, Bangor University in Wales and the Technical University Munich in Germany. We'll be delivering in Q1 to them. I mentioned earlier we became the first private fusion company to use our own reactors for tritium production. And also, we're building a network of international partners to help build up our isotope capability, because we don't have all the resources we need yet to be able to produce isotopes independently. So we have to work with international partners where the infrastructure already exists. So we call this airdropping, where we can take one of our systems that we own and operate in a partner's facility to begin delivering isotopes to the medical community. And then besides the facility that we have in Bristol, in order to build a very high flux array, the shielding that's required to build that array is unfortunately too heavy to build in Bristol. The facility we have in Bristol has the foundation of the business park that we're in can't take the weight. So we currently built a 100-ton bunker. But in order to get into 14 MeV neutron production in an array in a high flux environment, we need far more shielding. But we were lucky at the Berkeley Science Park, about 30 minutes north of Bristol. It's a decommissioned fission reactor. And when it was privatized, the company or the group that found it, the Chilton Vital Group, found a 7-meter deep concrete pit that was never used. It was originally intended for storage of fissile waste, but it was never used. And we're looking to move in there in Q1 of next year, where we'll build our first array of DT, high energy reactors. And it's our hope or our ambition that within next year, that facility will be the highest flux or the highest density continuously operating DT fusion irradiation facility on the planet. That's what we're aiming for. So I hope I've kept that short and sweet, and I am more than happy to discuss or answer questions. Thank you very much.
Talmon, thank you very much indeed. Again, just fascinating to see, all the different components going on around fusion. I think, you mentioned there a few of those grand challenges. There are certainly a few things still to kind of iron out and overcome. But that the tritium breeding breakthrough there, I think, is signs that there's things happening now to overcome these challenges and really propel the industry forward. It's great to see. I just want to very quickly hone in on that before we move to Q&A. One of the most striking things that Astral has done is that tritium breeding in a compact device. Does that is there anything to sort of imply there around future sort of decentralized tritium breeding potentially, and how that might kind of impact the economics of DT fusion? Any thoughts on that?
There's actually a bunch, but first of all, tritium breeding will have to be decentralized. In that every fusion reactor that is operating commercially will have to have a tritium breeding blanket of some sort. The question then leads to will these fusion companies have to build a tritium blanket that can exceed a tritium breeding ratio of 1, meaning that they can produce more tritium than they can consume? The challenge there is that with a lithium blanket, and there are various different types that different fusion companies are looking at. The physics limits that breeding ratio. Typically, it's kind of in the range of a maximum theoretical range of around 1.3. I've heard some people say 1.8. I don't know where they're getting their numbers, but typically around 1.3, which means the error margin is about 30%. Now, what's interesting is, and some of the fusion companies that we've been speaking to are beginning to think, maybe don't be so hard on themselves. If they can get to a tritium breeding ratio of 0.8 or 0.9, can they then work with a technology like ours or a different kind of technology to make up the gap, make up the difference? And this is actually, there is a parallel to this within the kind of oil and gas or coal industry, where you'll find a power generating station using some of the power from that station, let's say 20%, 30%, to power additional services relating to the system. So in that case, we would potentially be able to use a smaller array of our systems that isn't energy producing, but focused on highly efficient tritium breeding. And this leads to also what we believe is to in order to really get the most tritium out of that kind of array, use a little bit of fissile material and perhaps a transmuting waste, make that an additional revenue service to really get that tritium breeding ratio up. And I'll explain why that's important, which is that if pure fusion has a maximum tritium breeding ratio of 1.3, but if you're able to get 100 times neutron multiplication from fissile material, suddenly you can design a system where that tritium breeding ratio is actually 100 to 1, not 1 to 1. And so that's really where you can have a compact supporting system adjacent to a fission power plant that is really able to make up that gap of 20%. And if it's really well designed, you might be able to eliminate the lithium blanket from the fusion reactor and focus on actually optimizing for energy production, because that's what I consider actually the fifth grand challenge of the fusion industry is can fusion produce power economically relative to other power sources that we have. Fusion is fusion will never replace all power sources. It'll have to find its niche within the broader power community. But it will have to get over the can it be done economically? Probably it can. I really hope so. I'm a big fan of fusion, obviously, but it's still a challenge. So tritium will be decentralized from that perspective.
Interesting. Thanks, Tom. And just very quickly to pick up on one of those points there, around the economics then. As a company, one of the few companies kind of delivering a commercial outcome from fusion, is there anything you've learned around building a fusion business that can be applied to, potential fusion power companies who are kind of getting their ducks in a row and getting that technology ready to go now and kind of will be at that process potentially, in a few years? Anything, I know they're very different applications, but anything you've learned kind of that can be applied kind of as a frontier fusion business?
I'd love to take credit for saying I've learned it, but I haven't learned it. I mean, David already gave a great presentation and showing that there are many other applications that the research that goes into fusion can result in commercial opportunities and research or other industries and other industries. I think rather to say that I've learned, but rather the 50 plus fusion companies around the world are either ahead of the game or following along, realizing that on the path towards fusion energy, they will have to find other commercial applications to be able to keep the company going. About 10 billion has been invested into the fusion power sector from venture capital and private equity to date. It sounds like a big number, but if you look at some other industries, that's like a month's spend in the let's say the oil and gas industry, or even if you look at the amount of money that's been put into AI or even other industries. And so if we switch the narrative on 10 billion is actually not a lot. In order to really survive and thrive in this next wave of fusion development, companies have to be revenue focused and they have to build solid businesses. And that's what Tokamak Energy is doing. That's what Astral's doing. That's what a few other really good fusion companies are doing. And what we might see in the next, let's say, 5 to 10 years is those that were ahead of the game surviving, and those who ended up following and not being prepared for this shift might fall off.
Mm. Yeah, interesting. David, I think that kind of goes to one of your points there around how you said, you've made it a real focus to kind of work with others around this technology, kind of sharing applications and things learned as well. I'm sure that's really important. And I think it's one of the great things around these nascent industries that have so much potential is at this stage, there's a lot of cooperation there around learning from each other and realizing that it's in kind of best interest, I suppose, to share that learning as well.
Yes, the fusion is too big a challenge for one single company to do it all. So we have to find the right partnerships, the right spin-off technologies, the right commercial opportunities as we go.
Yeah. We've got a few more minutes for questions. Please do pop any in that you have specifically for David and Talmon into that Q&A session. I'm sure there's a lot to unpick there. I can see a question in the chat now. It's for yourself, David. It's from Kamar Khan. Kamar says, fantastic presentations. Your copper buzz bars are of interest. Can you please describe a little more how you get more from less? Also, how is the business currently funded?
Oh, right. So the buzz bars we make are made from high temperature superconducting material. So that material has a conductivity 200 to 500 times better than copper, and therefore you can have much more compact buzz bars, and they are very suitable for high current, low voltage transmission, and DC transmission in particular. So they do offer huge weight savings, energy savings, size, volume savings within data centers, and in a range of other industrial applications that need a lot of DC. Business is currently funded partly by commercial income now, but primarily still by investors. And initially, this was private individual investors from the UK and Europe. More recently, it's been corporate strategic investors who see some synergy between our products and the markets they currently serve. So we're building a lot of relationships now with what we would call go-to-market partners. We have the technology, they have the market opportunity. In combination, we can develop the technology to reach large markets.
David, thanks very much. Kamar, feel free to come back there if there's anything else, any more clarification you want there. Other than that, I've just got one final one then for you both. I think it's fair to say that, in many aspects, the UK is a leader in fusion. We've seen that around R&D in quite a few different applications of fusion. If the UK wants to be a serious kind of fusion nation into the future post 2030s, what are kind of one or two things that both government and the industry now has to get right? Right now, where should those focuses be around kind of those grand challenges, to kind of really keep this momentum going forward, as we start to hopefully see, even net electricity as well, generation through fusion as well as other applications. Any thoughts on that to kind of close out?
David, I would just say I think that the UK is doing a good job. I think that the UK is a leader, has been a leader, and will continue to be a leader. We've got we've got the STEP program. UKAEA has their Liberty program, which is I think the world's best funded tritium breeding program, and just really keep going.
Yes, I agree. Government should keep going to ensure that it does keep growing. I think it's up to companies like Astral and Tokamak Energy to demonstrate economic impact from the technologies that are being developed for fusion, and that will reinforce the government's enthusiasm.
Yeah, well said. David, Talmon, thank you very much indeed. We're just about out of time. Really appreciate you guys joining and sharing your thoughts. Two really, really interesting presentations. Again, like I've said with quite a few of these webinars, I think watch this space is what I'd say, because there's a lot more conversations to be had. As I mentioned, fusion will be a big part of our Foresight event in February. And Talmon, I think you will be joining us there as well to kind of go into a bit more detail around that fission fusion hybrid aspect of the equation. So it'll be great to have you there. If you are interested in more conversations around this, then do keep an eye out. We'll be doing a lot more in this space around, you know, all aspects of new nuclear as well, fusion, SMR development, all of it. So do keep an eye out. But for now, I'll say thank you very much indeed for joining us from the floor and for your attention. Really, really interesting. And we do hope to see you again in the future for more webinars and more sessions. So thank you very much, everyone, and take care. Bye-bye.
Thank you.